for the invitation. So thank you for the invitation. It's a great pleasure to give a talk here. So as you said, today I'll be talking about Hofer distance on Hamiltonian isotopies of Lagrangian submanifolds. So I will start with a quick overview of basics of symplectic geometry, and then move on to some context and explain my result. And in the second part, I will dive more into technical details of how we construct the invariants I'm using in my proof. So let's start with, some definitions of symplectic geometry. So a symplectic manifold is a smooth manifold M equipped with what we call a symplectic form, omega, which is a non-degenerate closed two-form on M. So here closed means that d omega is equal to 0. And you can check that a symplectic manifold is always of even dimension to n. And the non-degenerate condition is equivalent to say that omega to the power n is a volume form. By the way, feel free to ask questions during my talk, or tell me if I go too fast. So here are some examples of symplectic manifolds. So R2n equipped with the form sum of dxi wedge dyi, where we have chosen a basis x1, xn, y1, yn of R2n. This example is the most standard one, as one can prove that any symplectic manifold is locally isomorphic to this one. So you can find charts in which the symplectic form becomes this one. Another example is any oriented surface equipped with an area form. Or given any smooth manifold, you can look at its cotangent bundle. And if you take coordinates qi on the base M and coordinates pi on the fiber, then the form given locally by sum of dpi wedge dqi is a symplectic form. Another example is CPN equipped with the Fubini study form. So as I said before, every symplectic manifold is of even dimension, but there are some even dimensional manifolds that do not admit any symplectic form. For instance, if you take S4, then you know that the second theorem cohomology group of S4 is trivial. And so you can never find a symplectic form, like a two-form, closed two-form, whose second power would get a volume form. That's not possible. So not symplectic. Another example is S2 times S4. So here, even though the second cohomology group is non-trivial, you can check that for omega a closed two form, you will never have like closed two form. You always have that omega to the power 3 is equal to 0, so it cannot be symplectic. Okay, so now that we know what is a symplectic manifold, I will define an important class of submanifolds called Lagrangian submanifold. So we say that a submanifold L is Lagrangian if it's of dimension half the dimension of M, so here dimension n, and if the symplectic form, the restriction of the symplectic form on L vanishes. So as an example, if we take R2n, and if we look at the space generated by the x1, xn, then you can check that the symplectic form vanishes on it. And so it's a Lagrangian submanifold. Or if you take any simple closed curve on an oriented surface, since the form omega is an anti-symmetric form, when you evaluate it on one-dimensional submanifold, it will always vanish. And so any simple closed curve is a Lagrangian submanifold inside a surface. Or also, you can check that the zero section inside a cotangent bundle is a Lagrangian for the standard symplectic form I described before. Okay, so now that we have defined our manifolds, we can define maps between them. So we will say that a diffeomorphism between two symplectic manifolds M and M prime is a symplectomorphism if it preserves the symplectic form. Yes, so an important kind of symplectic diffeomorphism that we will be interested in is the case of Hamiltonian diffeomorphisms. So pick smooth function on the circle S1 times M to R. Then, since the symplectic form omega is non-degenerate, you can find a unique vector field xht such that omega of xht dot is equal to minus d of ht. So this is because omega is non-degenerate, so it establishes a pairing between yes, like you can represent any one form with a vector field. It's pairing vector fields with one forms. Okay, so now that we have this vector field xh, we can look at its flow, and we will say that the time one map of this flow is the Hamiltonian diffeomorphism generated by H, and we will denote it by phi H. Let me maybe give a motivation behind this definition. So if we look at T star M equipped with the symplectic form omega equal to sum of dpi wedge dqi, where this is coordinates on M and this on the fiber. Then you can view this T star M as the phase space of a particle, for instance. So the Qi would be the position of your particle, and the Pi is the speed. And if you take a function h on S1 times M to R, and you compute this vector field xh and integrate it, you would get the following equation for the flow. So you get q dot I is equal to tht over dpi, and p dot I is equal to minus tht over dqi. So maybe if you've learned some
So it's
classical
defined on
mechanics,
T star M, right? Not on M.
yes. Yes, sorry, here H is on T star M. You're right. So here maybe you recognize the Hamilton equations, which are an equivalent formulation to Newton's equation of movement. So this has interest in, like, if you're studying classical mechanics, those are interesting diffeomorphisms. And the function h here represents the energy of your system. So a few remarks about Hamiltonian diffeomorphisms. First of all, there could exist several Hamiltonians generating the same Hamiltonian diffeomorphism. For instance, you can shift your function by a constant. It will not change the vector field because it's defined with, like, the vector field is defined with dh, so you get rid of all constants. And also there could be several isotopies with the same endpoint diffeomorphism, but generated by different vector fields. For instance, if you take the two sphere, you can take a rotation around its axis. One can show this is an isotopy of Hamiltonian diffeomorphisms. And if you rotate by an angle of 2 pi times t at time t, then at time 1 you would recover the identity map. And so you get two different isotopies for the identity. You can take this, like, this whole rotation, or just stay fixed at all time. Okay, so I didn't explain why Hamiltonian diffeomorphism is symplectomorphism. So we need to check that it preserves the symplectic form. So the flow of xt, if you take a vector field on M, then its flow preserves the symplectic form if d over dt of phi t star omega is equal to 0. And this is equivalent to saying that the Lie derivative of omega along x vanishes. But this is equal to d ixt plus ixt d omega. And we know that omega is closed. So this is equivalent to say that ix omega is closed. And if you recall, if you remember the definition of the Hamiltonian vector field xht, xht was defined such that ixt omega is equal to minus dh t. So this is exact, in particular closed. So therefore, any Hamiltonian diffeomorphism preserves the symplectic form and is a symplectomorphism. The converse is not always true. For instance, when you have a non-trivial first cohomology group, then you could have a vector field which preserves the symplectic form, but such that ix omega is not exact. For instance, if you take the torus T2, so T2 equipped with omega, which is just the standard area form on the torus. If you take a translation on the torus, it will preserve the area, but one can show this is not a Hamiltonian diffeomorphism. Okay, then one can show that the set of Hamiltonian diffeomorphisms is in fact a group for the composition operation. So if you take a Hamiltonian diffeomorphism generated by a Hamiltonian H and another one generated by K, then their composition, you can show it's also a Hamiltonian diffeomorphism generated by the Hamiltonian we denote H sharp K, which is given by this expression here. And also for the inverse map, if you have a Hamiltonian diffeomorphism generated by a Hamiltonian H, then its inverse is also a Hamiltonian diffeomorphism generated by this Hamiltonian here. So now I will show we can define a distance on the set of Hamiltonian diffeomorphisms. First of all, we define a norm on the Hamiltonian function itself, which is the integral over time. Oh, by the way, I define my Hamiltonians to be functions from the cycles time m to r. I could have taken, instead of the circle, the interval 0, 1. Here I'm just asking them to be periodic, but it's not a really important condition in what follows. So yes, so the norm of h is the integral of the oscillation of h over time. And yes, the oscillation is defined as the max minus the minimum of h. Then we can define a norm on the set of Hamiltonian diffeomorphisms by taking the infimum of the norm of the Hamiltonian function h over all Hamiltonian function h that generate phi. This norm induces a distance called the Hofer distance, defined in the following way. The distance between phi and psi is also the distance between the identity of and psi inverse, and it is defined as the Hofer norm of psi inverse. Okay, so now that we have all those basics down, I can explain a bit my results. I will start with some context. So we are considering, well, are there some questions up to this point, or is it fine? Okay, so we're considering a symplectic manifold M, possibly with non-empty boundary, and a Lagrangian submanifold L0. So now that we possibly have boundary, we need to restrict a bit the Hamiltonian diffeomorphism we will consider. So we will ask them to be compactly supported in the interior of M. So this is why there is a small c here in my notation for compactly supported. And we will look at the set of Hamiltonian isotopies of the Lagrangian L0. So yes, I didn't say it before, but any symplectomorphism sends Lagrangian submanifold to Lagrangian submanifolds. This is because the symplectic form vanishes on the Lagrangian, and since phi preserves it, it will also vanish on the image. So the image is also a Lagrangian submanifold. So this is basically the set of all Lagrangians that are Hamiltonian isotopic to L0. And this set can be equipped with a distance induced by the Hofer distance that we define as d of L prime is equal to the infimum of the Hofer norm of phi mapping L to L prime. So
Sorry,
yes.
just one precision. So what do you mean by a symplectic manifold with non-empty boundary? You mean on the interior there is a symplectic form, and what do you suppose on that?
Yes. So yes, a symplectic form on the interior, and you have a boundary.
Okay.
So for instance, you can take the disk equipped with the standard diarrhea form. This is a symplectic form with boundary. Yes, so very little is known about this distance, and for instance, we can ask if it is bounded. So if this set L of L0 m omega is has finite or infinite diameter for this distance. So there are a few cases where we can answer this question. For example, if you take, so your symplectic manifold is R2, and you look at a circle inside R2, then we know it is bounded. And this is actually an easy result that I will try to prove to you later. Then Khanevsky showed that if you take for the Lagrangian the diameter of the unit disk, so the symplectic manifold is the unit disk and the Lagrangian the diameter, then this distance will be unbounded. He also showed that the distance is unbounded when the symplectic manifold is an annulus and the Lagrangian a non-contractible circle inside the annulus, or when the Lagrangian is a circle bounding a disk of area more than half the area of the annulus. And then in 2013, my advisor, Seyfaddini, generalized Khanevsky's result about the diameter inside the disk to higher dimension. So if you take for your symplectic manifold the Euclidean ball in any even dimension Euclidean space, and for your Lagrangian, the standard Lagrangian, so the one, so in R2n, you have this Lagrangian that is generated by the x coordinates, and then you take its intersection with the Euclidean ball, then the Hofer distance for the set of isotopies of this standard Lagrangian will be unbounded. Yes. Okay, so this question of unboundedness of the Hofer distance for sets of isotopies is still unknown in most cases. For instance, if your Lagrangian is the equator inside the two-sphere, this has been an open question for more than 20 years. And some people have made some progress in trying to find ways to tackle this question, but never found an answer. And it's also open for a circle inside the unit disk. So maybe, well, I was planning to show this first result, but maybe I should already state what my result is. So what I showed is, where is it? Yeah. So in my case, I will consider as a symplectic manifold the unit disk equipped with the standard symplectic form, so the standard area that you normalize so that the disk has area 1. And we take an integer greater or equal to 2 and we consider a disjoint union of k embedded smooth closed curves bounding disks that all have the same area, lambda greater than 1 over k plus 1. So I drew a picture here. So you have the disk here, so it's for k equal 3. You have 3 circles inside your disk, all bounding disks of the same area lambda, and we ask lambda to be greater than 1/4, so that the area of the complement of the disks is smaller than lambda. This is important. And so we are considering this union of 3 disjoint circles. This is our Lagrangian L0. And the theorem is that the Hofer distance on the set of isotopies of this disjoint Lagrangian is unbounded. Okay, so maybe to get a better idea of how this Hofer distance works, I wanted to prove this result about the distance being bounded for a circle inside the plane. So first of all, I will show a small result. So consider the following. You look at the plane R2 with coordinates y and x, and we will take a square of length a. So okay, so let's say this is 0, a, and we define a Hamiltonian h of xy equal to a plus epsilon times y. Then you can compute the vector field, the Hamiltonian vector field generated by h, and the flow of this vector field, and you get a Hamiltonian diffeomorphism phi h, which acts as a translation by a plus epsilon in the x direction. So it will map this square to another square on the right that starts at a plus epsilon. And then if you take a small box around those two squares inside the plane, and you cut off h there so that it becomes 0 outside this box. So we get a Hamiltonian h whose oscillation is, so this h is 0 here. It depends only on y, and it's equal to a plus epsilon times a near this line here. So the oscillation of h is equal to this. And so what this shows is that you can displace this square to the other one with a cost of Hofer energy, which is around a squared, which is also the area of the square. Okay, so now if I take any topological circle inside the plane of area A, and I take another one which is disjoint from this one over there, also of area A, I'm claiming that I can find a Hamiltonian diffeomorphism mapping the first one to the second one with energy, with Hofer energy also around A. How do I do this? Sorry. I take a small neighborhood of this first circle, another neighborhood of the second one, and I join them with a small tube. And then I'm claiming that I can conjugate the picture I had above with the picture I have below. Well, I also need to, maybe I need to smooth the corners of my square here. Okay, and then I can find a map psi that map the picture above to the picture below. That is also Hamiltonian diffeomorphism. This one could have really large Hofer energy, but what I get in the end is that if I take, so if I take psi by h psi inverse, it will map this first circle to the second one. And the Hofer norm of this is actually equal to the Hofer norm of phi h, because the Hofer norm is conjugation invariant. And therefore, this is around A. So this means that I can always displace my circle to another one bounding a disk of the same area for a cost which is the area of this circle. So now I can prove the result I had here. If I take a circle inside the plane and I have my circle, and any circle that is Hamiltonian isotopic to this one, if the second circle is disjoint from it, then I can move from one to the other and stay at a distance a. But if, so we are fine if the two circles are disjoint, but if they intersect each other, then what I can do is, so this is L0, this is L. I can find some circle L prime disjoint from both of them. Then I map L0 to L prime with an energy equal to the area of my circle. And then I move L prime to L with an energy also A. And so this picture shows that the distance on L0 R2 omega is bounded by 2A, where A is the area of the disk bounded by L0. Okay, do you have questions about this, or is it clear? Okay. So this was to show that the distance is bounded, but in all the other cases I presented you, the distance is unbounded. And to show this, Khanevsky used quasimorphisms. So I will define what a quasimorphism is. You take a group G. A quasimorphism of G is a map from G to R that satisfies that the supremum of the difference between QGH minus QG minus QH is bounded for G and H in G. So this supremum is called the defect of Q. So what this means basically, you see here that if this quantity was identically zero, then Q would be an honest group homomorphism. So here what we ask is for Q to be a homomorphism up to a bounded error, D. We will say that a quasimorphism is homogeneous if it behaves well with respect to taking powers of an element. So if for all G in G and N in Z, Q of G to the N is equal to N times QG. Now, if you have a quasimorphism Q that is not necessarily homogeneous, you can always homogenize it by the following formula. You define mu of G as the limit when n goes to infinity of Q of G to the N over N. One can show that this is well defined because since we have the quasimorphism property, the sequence Q of G to the N is subadditive up to a constant. And so one can use Feketti's subadditive lemma to show that this limit here converges. And yeah, and it's straightforward to show that now that we have taken this limit, mu becomes a homogeneous quasimorphism. Okay, so now I will state like the strategy that Khanevsky used to show that the Hofer distance on the set of isotopies of a Lagrangian is unbounded. For this, he defines the stabilizer of your Lagrangian L0 as the set of all Hamiltonian diffeomorphism fixing L0. Here it's not necessarily pointwise. You only need it to have image L0. And so suppose you have a non-vanishing homogeneous quasimorphism R on, on the group of compactly supported Hamiltonian diffeomorphism of M that is also Lipschitz with respect to the Hofer distance and that vanishes on the stabilizer of L0. then this implies that the set of isotopies of L0 has infinite diameter for the Hofer distance. So I will prove this proposition now. So suppose we have such a quasimorphism R from Ham C M to R, and we made the assumption that it's non-vanishing, so there exists some phi such that R of phi is non-zero. And what we claim is that the distance from phi to the n of L0 and L0 goes to infinity as n goes to infinity. Indeed, this distance here is defined as the infimum of the norm of psi for psi such that psi phi n L0 is equal to L0, right? And so then we will try to bound from below the Hofer norm of such a psi. So since our quasimorphism R so we made the assumption that it is Hofer-Lipschitz. This gives us that there is a constant k such that the Hofer norm of psi is greater than k times R of psi. And then we use the quasimorphism property to say that this is greater than k times R of psi phi to the n minus R phi to the n minus the defect of R. And then, so by hypothesis on psi, we have here that psi phi n fixes L0. So psi phi n is in the stabilizer of L0. And therefore, by assumption on R, this quantity here vanishes. And we also made the assumption that R is homogeneous. So this is equal to n times R phi. And we end up with the norm of psi greater than k times n R phi minus d. And since we know this is non-zero, this goes to infinity. And this concludes the proof, because then the distance goes to infinity. Okay, so we will try now to apply this strategy to show our results. So we will need to find a quasimorphism that vanishes on the stabilizer of our union of circles that is homogeneous, Hofer-Lipschitz, and non-vanishing. So to do this, we will do the following. We embed the disk into a sphere S2 of area 1 plus S, where S is a real number in this interval here. So let me maybe explain this condition here. Basically, so we had this disk here, we're embedding it into a sphere. And so we have our circles of our disks of area lambda. And the condition on S is so that the complement still has area less than lambda. Okay, so now we denote by BI the connected components of the sphere minus our union of circles. We denote by AI their area and by KI their number of boundary components. So basically what we have here we have that B1 to BK are disks with AI equal lambda and Ki equal 1. And BK plus 1, it's this surface with K boundary components. So we have, oops. Okay, so maybe in the, yeah, K plus 1. Yeah, maybe it's not a great notation for the number of boundary components, but well, it has K boundary components, and its area is less than lambda. Okay, so then we will define some number eta of s with this formula, so that for all I, the following equation holds. So basically, since almost all connected components are disks, this Ki here will be 1, so this will vanish, and you only get that the area of the disk is equal to lambda, so this is trivial. And when when I is equal to K plus 1, you define this eta, so you know that the area AK plus 1 is less than lambda, and so you define this eta so that so that this equation holds. And this gives you this formula here for eta. Such configuration of circles inside the sphere, we call that an eta S monotone Lagrangian link. So it's a link for which all connected components of the complement satisfy such an equality is called an eta S monotone Lagrangian link. And this was defined by Cristofaro, Gardiner, Humilière, Mack, Sopan Seyfaddini, and Ivan Smith. And they showed that given such a link, you can construct a spectral invariant, CL, that goes from smooth maps on S1 times S2. So this is basically the set of Hamiltonian functions to R, satisfying that this invariant is Hofer-Lipschitz. So the difference of CLH and CLK is less than the norm of H minus K. You can also, so there is a property called Lagrangian control, which enables you to compute those invariants when your Hamiltonian H is constant on every component of the link. And then it gives you that the value of CLH is basically given by averaging your Hamiltonian on the components of the link. It's also homotopy invariant. So if I take a Hamiltonian diffeomorphism of the disk, I can pick a Hamiltonian function supported inside the disk generating phi. Then I embed it into the sphere, and I compute CL of H inside the sphere. Then I claim that this computation will not depend on the choice of H generating phi. And so I can define CL of phi for Hamiltonian diffeomorphism phi as this value CL of H. And also, they show that this invariant is a quasimorphism. So now we're one step closer to finding our desired quasimorphism. As of now, it's not vanishing on the stabilizer of our Lagrangian link. So we will need to vary this parameter S here and to take a linear combination of those spectral invariants to get a quasimorphism vanishing on the stabilizer. So to do this, I will apply a theorem by Francesco Morabito. So he showed the following. If you have Hamiltonian diffeomorphism in the stabilizer of L0, so this means a Hamiltonian diffeomorphism that maps the union of circles to itself, then there is a way to associate to such a diffeomorphism an element of the braid group with k strands. So let me draw a picture. I have my disk, and I have k circles inside the disk. And I have my Hamiltonian diffeomorphism that fixes them, fixes it fixes the union actually, so it could permute the circles. Like this is L1, L2, L3. We know that phi of the union is equal to the union, but it could, for instance, map L1 to L2, or yeah, it could permute them. So now I take Hamiltonian H generating phi, and I look at the isotopy phi t x h t, and I look at how the image of those three circles will evolve. So, for instance, if you could do something like that, we know at time 1 it will be mapped to those three same circles. So so if I look at this isotopy phi t x h t, it could do something like that, for instance. And you see that this naturally describes you a braid with three strands here. And I claim that whatever H I choose generating phi, I will always get the same braid type with this construction. Okay. So now we do as before, we choose two real numbers S1 and S2 in this interval and embed the disk into spheres of area 1 plus S1 and 1 plus S2. And we get the link spectral invariance that we defined before. So Morabito showed that if you take phi in the stabilizer, then the difference of those invariants with two different parameters is given by the difference of the eta S1 and eta S2 over k times the linking number of the braid type of phi. Maybe I should remind you what the linking number of a braid is. It's basically the counted sign of such crosses in the braid diagram. So anyway, this shows that the difference of those spectral invariants on the stabilizer is only determined by the braid type of phi and is proportional to the difference of eta S1 and eta S2. So now that we have this, we can build our quasimorphism that will vanish on the stabilizer. So we choose four different real numbers S1, S4 in this same interval. We embed the disk into different spheres of area 1 plus S1 to 1 plus S4. And we end up with those Hofer-Lipschitz quasimorphisms CL0SI. And we homogenize them to get quasimorphism mu I and mu 4 that are homogeneous this time on the set of compactly supported Hamiltonian diffeomorphisms of the disk. So now, by Morabito's results, we know that the difference of those quasimorphisms is on the stabilizer of L0. And so if we take a linear combination of those four quasimorphisms with the following coefficients, like eta 4 minus eta 3, mu1 minus mu2, minus eta 2 minus eta 1, mu3 minus mu4. So we chose here those coefficients exactly so that when you when you evaluate this on an element phi of the stabilizer, this will vanish. Okay, so now that we have our homogeneous quasimorphism that vanishes on the stabilizer, that is also Hofer-Lipschitz, the only thing remaining is to show that it's not identically vanishing. So to do that, we use the following statement. So by Christopher Gardiner, Humilier, Max, Seyfaddini, and Smith, they showed that when you homogenize the link spectral invariants, their value will only depend on the number of components of the link and the constant eta. It will not depend on the particular configuration of your links. And so we can pick any other Lagrangian link Li, which has L prime I, sorry, which has also k components and monotonicity constant eta Si, which is the same as before. And then they will define exactly the same quasimorphism. So we will construct such links in the following way. For a real number A, we denote by Ca the circle of radius square root of A center at the origin. So that this circle has bounds a disk of area A. So I drew a picture here. This is C lambda in the middle, bounds a disk of area lambda. And then you take, for each I, you consider the circle bounding a disk of area 2 lambda minus 2 eta I. And since eta 1, eta 2, eta 3, eta 4 are all different, those circles are disjoint. As you can see here, the green one and the red one are disjoint. Then you embed this picture into a sphere of area 1 plus Si, and you complete those two circles, C lambda here and C2 lambda minus 2 eta 1, into a link with k components. You space them so that each time the area between two of them is equal to lambda minus 2 eta 1. And so we get an eta 1 monotone link with k components, L prime I. And so, as we said before, we can compute our quasimorphism using those new links instead of the ones we had before. And so if we take a Hamiltonian H on D, which is equal to 1 on the circle C2 lambda minus 2 eta 1, and supported in a small neighborhood of it. So as I said before, the other circles for eta 2, eta 3, and eta 4 are disjoint from this one because they have different values of eta. So we can pick the support really small so that it will be 0 on the other circles. So that when you compute the value of mu L1 prime of H, this will be 1 over k, and it will be 0 for all the other ones. So this will vanish, this will vanish, it will vanish, and you end up with R of phi H equal to eta 4 minus eta 3 over k, which is non-zero. So this completes the proof. I guess I'm done with the proof of the main result, so this ends the first part of the talk. So if you have some questions.